In this video, I am going to illustrate about intrinsic impedance, the amount of resistance the electromagnetic wave experiences when it travels through any medium, let it be a conducting medium or non-conducting medium, through a free space. And I am using the differential equations, a wave equation which is derived from the Maxwell equations, to demonstrate and to showcase what is the mathematical relationship of this intrinsic resistance impedances with respect to the transverse component of, that is, H and E. So we know that the differential equation of wave equation, if you are not clear with that, you can watch my previous videos where I clearly illustrated all the different easy way to come onto the wave equation from the Maxwell laws. So wave equation states that, so using wave equation we can represent an electromagnetic mu epsilon E square by T square equals. Here we use permeability, conductivity and permittivity of a medium, and we have E, the magnetic field and electric field, both are transverse functions. So E and H both are orthogonal, and let us assume that the electromagnetic wave is propagating along the Z axis, and the component of E is varying along the electric field is varying along the X axis, and the component of H is magnetic field is varying along the Y axis. And this is the differential form of the wave equation, and we can express this wave equation in the polar form. So the same wave equation we use, instead of d by dt we use j omega. That's the easiest way to convert this differential form to a polar form. So mu sigma, so j omega E minus mu epsilon, so j omega d square E equal to 0. So from this function we can see that there are some common terms in here and here. So let's take it out and make it more simple. See, j omega mu, so you know that it's a j omega mu here and j omega mu here. So j omega mu sigma plus j omega epsilon E equal to 0. Let us represent this function as the gamma square. So naturally, let us take it as equation number 1. So equation number 1 becomes E minus gamma square E equal to 0, where gamma is a propagation constant. It's a complex number. It has two terms, alpha and beta. So where alpha is the attenuation constant and beta is the phase shift constant. So let us take one electromagnetic wave, which is a sinusoidal function. It can be represented as a sinusoidal function. Let's take it as, see, this is a very the frequency is very high, but as it the time progresses, we can see that that the amplitude is slowly coming down, and also the phase is increasing a little bit. So these two the features can be expressed with alpha and beta. So the propagation constant, because the amplitude and phase is no longer a constant when it propagates through any mediums, that the both will change. So both the amplitude and the phase changing is represented using the gamma. So by looking at this function, we can see that this is E, and we know that E is varying along the x-axis, and the wave is propagating along the z-axis. So let us take this E as the function of Ez, and it is varying along the unit vector that is taken as x cap, because this is oscillating along the x-axis, but it is propagating along the z-axis, but it has no y component, and the wave propagation is only through the z-axis. So let us substitute this in the previous expression. So this become E of x is minus gamma square E of x set equal to 0. So delta square minus gamma square E of x is set equal to 0. So it is clear that it is a homogeneous differential equation. So when we solve a differential equation, and we can see that it has only z component, and if you represent it is in a pure differential form, we can write it as delta z square minus gamma square this ex z ex of z is 0. So from this we can take it out. Sorry. So this is a second order the homogeneous differential equation. Because why it is homogeneous? Because we don't have any, so on the right hand side it is 0. So if you solve this the homogeneous equation, we will get the solution has two parts. One is complementary function and a particular integral, and this the complementary function is the transient term, and this particular integral is a steady state variable. It's a steady state. As time tends to infinity, this term produces a constant amplitude. So let us take it as this as equation number 2. The solution of equation number 2 is E of x, that is propagating along this z-axis, has two terms. Let us take it as E naught e power minus gamma ez plus E naught dash e power gamma ez. So this one is the particular integral, and this is the complementary function. See, looking at this complementary function, we can see that as time propagate, this amplitude is increasing, but here as time propagate it will produce a constant time, that is E naught. So particular integral function, that is E naught e power minus gamma is look like this. Yes, always that is C0, start from E0. Steady time. But if you look this function, complementary function, so that is E naught dash, that is the amplitude, another amplitude of gamma is set, will look like this. So as time increases, the amplitude decreases. But let us assume that this terms will eventually dies out. So the only thing it eventually died out when E naught dash equal to this we have also, because finally we have only one steady component, that is E naught. The amplitude of that component is E naught. hence the solution E of x z can be represented as E of x. That is the solution of the homogeneous differential equation E of x is E naught e power minus gamma z. So from this expression, it is clear that the steady component of E of x has E of x is the steady as time propagate. And now I am going to express this E of x that is propagating along this z-axis in the time varying component of the complex form. So it can be represented as E of x is said. It's also functional, not only the space, it's also functional time t. So this becomes E of x is z component, this component, E of x is z component, and the complex function E of j omega t, and that is varying along the x-axis. So we need to use the unit of the coordinate system x cap. And so why? Because we are using e power j omega t. This is exponential form of e power j omega t. So this is nothing but cos omega t plus j sine omega t. So it has two components, real part and imaginary part. So now let us take what is the real part of this function. So e of x is like t. That is what is the real part. So looking at the complex function, we have two terms. We have one constant term and we have an exponential term which is in j, and we can separate those two terms and we can represent this function as real part of e naught e power minus alpha z into e power, so we have j omega t and minus j beta z e power j omega t minus beta z into x. So that is the unit vector. So we can represent this as this function as e naught e power minus alpha z. What is cos j theta? So that is cos theta plus cos omega t minus beta z plus j sine omega t minus beta z the x. So this is a complex function. If you separate the real part, so the real part is e naught e power minus alpha z into cos omega t minus beta z into x. So this is the electric field component. So this along this axis, and it is also a function of time. Now similarly, if you look into this representation, so electromagnetic wave that is propagating along this axis, it has two components, x component and y component. X component is the electric field and the y component is the magnetic field. So how to represent in the similar way, how to represent an h term that is also propagating along this axis, and it's a time t. So let us take it as in a similar way we can represent h, because both are the transverse component. So this is suppose this is e, if it is h, this is moving along, and x, and this is along y. Now let us take it as h naught e power minus alpha z the cos omega t minus b z, so the y cap. Now have a very close look. We know that we have studied earlier that E is a function of V. So from where we got this